Okay, we have a series, and we're going to see if this converges or diverges. The way we're going to figure this out here is by factoring the denominator in the first place. We decide to factor it because it's squared, and when it's squared, that's telling us, hey, we could split this into two different fractions, n plus 1 and minus 1, into two different factors here, and eventually split it into two different fractions using partial fraction decomposition, which is something from the previous chapters. So the reason we're doing this is that we could actually split this into two different fractions. Once you have two different fractions, you could use the whole telescoping series method. So let's go ahead and use partial fraction decomposition on that thing. So because you have two factors, that means that, and they're linear factors. They're linear because this is n and this is n. You don't have anything squared in there. That means that you put each linear factor under each of these two terms. You have a and you have b. One gets n plus 1, the other gets n minus 1 in its denominator. And a plus b must equal 2. So this is what we have. Now we can cross multiply a times n minus 1 plus b times n plus 1. We distribute. This is going to give us an minus a plus bn plus b. Now we can get the terms that have n together. That would be a plus b, which have an n, and then minus a plus b don't have an n. So we look at our numerator. Our numerator doesn't have any n's. That means that a plus b must equal 0. So a plus b equals 0. Because remember, this entire thing has to give us 2. And if this has an n, the only way to make that n go away is by multiplying by 0. And we know that this is the thing which is being multiplied to n. Therefore, a plus b must equal 0. So then we have only this left, and this has to equal 2. So we have negative a plus b equals 2. Now we have a system of equations. We subtract or add, the entire bottom equation. The a is subtracted, so a goes away. We have 2b equals 2. 2b equals 2. That means that b equals 1. And since we know that b equals 1, we plug in 1 over here. That would give us a equals negative 1. A equals negative 1. Now we could plug these back in. Plug them back in. Negative 1 and 1. Okay, now we have our brand new form of this thing here. Now it's split. Why did we do this? So that we could use the whole telescoping method. And I'm going to show you what that is. The telescoping series is where you plug in the numbers. You plug in the different values of the index we have. So this is going to be negative 1 over n plus 1. And we're adding 1 over n minus 1. This is equivalent to that. It's just dressed differently. Now, remember what a series is. With a series, we have a term, and then we add the next term, and then we add the next term, and then we add the next term, and we add forever if it's an infinite series, as it is in this case. So we start our first index at n equals 2. The index after that is going to be n equals 3. We're doing integers here. N equals 4, n equals 5. That's how it's going to work. This tells us what our first term that we're plugging in is going to be. And what's inside is always the same formula here. So what happens if we plug in 2? If we plug in 2, we get negative 1/3. Negative 1/3 plus 2 minus 1 gives you 1. This is 1. 3. Okay, we plug in 3. We get negative 1/4. 3 minus 1 is 2. So we add 1/2. 4. We get negative 1/5 plus 4 minus 1 is 1/3. Eventually, you're going to see the pattern. And this is negative 1/6. And we're adding 1/5 minus 1, which gives you 1/4. So at this point, you could see what the beginning of the series looks like. This is just the beginning. It would go on and on and on. Later, we're going to look at what happens by the end, because that's just as important. So first, we look at what happened here. What happened? Well, some things started to cancel out. This cancels out with this. 1? No, it doesn't cancel. Negative 1/4? Look, it does cancel. And so we can expect at this point that this pattern is going to continue. Like here we had our first term here in this location is what I mean. In this location within the formula got canceled out by the one in this location in this formula. You know, that one's going to be positive, this one's going to be negative, this one's going to be negative, that one's going to be positive. And so this pattern is going to continue. This one is the negative, and the other one is going to be positive. This one is negative, the other one's going to be the positive. But yet this one and this one are on the other side of the formula, and they're positive. So you're never going to get a positive to cancel with a positive, and besides, they're increasing. You know, the denominator is increasing. So these aren't going to cancel out based on the pattern that we're seeing. And if you don't actually see the pattern, you could just plug in n equals 6, n equals 7, and eventually you're going to see it. So it's only 1 and 1/2 that we should save, because they seem like they're not going away in this sum here that we're looking at. Our next important step is to continue this thing. Continue that thing to the behavior near the end. So just like it has behavior at the beginning, at the end, it's also the same formula, and there's addition here. There's addition going on. By the end, our last term is just this. It's always just plugging in n for n. You can think about it that way. N equals n, and that would just give us our formula. Negative n plus 1 plus 1 over n minus 1. Our second to last term is if we plugged in n equals n minus 1. We're plugging in n minus 1 wherever we see an n. So this would be 1 over negative 1 over n minus 1 plus 1 plus 1 over n minus 1 minus 1. Here we're plugging n equals n minus 2. Here we're plugging n equals n minus 3. So we have negative 1 over n minus 2 plus 1 plus 1 n minus 2 minus 1, negative 1 over n minus 3 minus, plus 1 plus 1 over n minus 3 minus 1. Okay, so this is how we're looking at the last 4 terms. we can now observe what cancels. What cancels? Here we have a -2. We have a -4, and -4, a -1, a -3, just n, we're subtracting 2 from this n, and that one's just left as it is. So now, just looking at this, look, this one cancels out with this one, and this one cancels out with this one. We can assume, following the same pattern, that this one canceled out with the previous one from over here. If you would actually plug n equals n minus 4, you would see that go away. This one would also cancel with the previous one. So the only ones that seem to have escaped cancellation completely, they will not be canceled, are this one and this one. Because how could they be canceled? How could they, right? It's like you're not going to find, the opposite of them way back in these terms back here. That's just not going to happen. So the way I see it, this one here survives and this one survives. So this is what our sum actually looks like. -1 over n and -1 over n plus 1. This will cancel out and that will cancel out because it's going to follow the same pattern where on the formula on this side you have a negative and the negative eliminates the positive. The negative eliminates the positive and so on. It's what's happening here constantly. This one's eliminating that one and so on and so on. So that's our terminal situation there with our sum. Now, all of this, the only reason we did this is so that we can now find what this series actually converges to. This is the telescoping series where we split it into two fractions and plug in values, see how it behaves at the end, see how it behaves at the beginning. Now we know. And now we could take the limit as n approaches infinity of this thing. So the limit as n approaches infinity of that is, as you can see, just the first terms. Because if you plug in infinity into here and you plug in infinity into here, these will go to 0. This will go to 0 because anything divided by infinity goes to 0. And so our limit goes to 1 plus 1/2, which is 3/2.